Hello, everyone. Thank you for joining us and welcome to our webinar. My name is Neil Foley and I'm the Applications Engineer here at RISE. Today, I'll be discussing automation and optimization with generative design. So I'll begin by talking about some of the general ideas around generative design, such as the problems it can help us solve and what it's most useful for. In particular, I'll be talking a bit about traditional methods of designing parts and the limitations of those methods. I'll also discuss the value of generative design in terms of how it can help streamline your design process and produce some optimal solutions. Then we'll look at generative design's relationship to the additive manufacturing industry and how each of these two can help you to get the maximum value out of the other. And finally, we'll look a bit more technically at what it takes to use generative design and some useful considerations. So first, let's look at the traditional method of designing parts. So here we have an image of a part created in SolidWorks using the drawing function. It has quite a few relations and dimensions that must be controlled, and this approach involves a lot of labor and expertise. The more complex and precise the design, the more labor and expertise will be required. Also, while an experienced engineer can produce very well-designed parts, it's rare that a typical approach will arrive at an optimal geometric solution. During the design phase, it's also necessary to consider the manufacturing method you intend to use and the capabilities and limitations that that method offers. This constraint can, in some cases, significantly limit the types of geometries that will appear in the design. Finally, in consideration of additive manufacturing, traditional manufacturing methods have largely shaped our traditional design approaches over the years. And since the development and adoption of additive manufacturing technologies, we've made major strides in our ability to produce complex geometries, but the design methods that can harness these capabilities have not yet fully caught up in popularity. So this is where the adoption of generative design can provide significant value. All right, so those were some of the limitations of traditional design methods. Now let's get into generative design itself, what it is and what it can offer. So generative design is a design approach being implemented into many CAD software suites that offers a lot of power. It uses computational methods to optimize the geometry or surface topology of your parts automatically. So essentially, you can enter a set of constraints and objectives into the generative design program, and it will gradually adjust the shape of the part until it finds an optimal solution to the problem you've set it. There is a great variety of settings and parameters that you can use to customize your requirements and generate precisely the right design for your needs. So in the image shown here, you'll notice that each version of the part design develops a gradually more organic surface as the process progresses. So generative design offers many benefits. One is automation. So by automating the design process around the basic constraints, it greatly reduces the need for mechanical expertise and making mechanical design more widely accessible. It also reduces the amount of labor required from designers. So generative design enables you to rapidly produce and iterate your designs as you refine your requirements. It also gives you control over all sorts of different parameters that you can choose to optimize. So for example, strength, it can be designed to be strong in a variety of load cases. So in some cases, you'll have a part that is expected to be used in a few different use cases. and each use case will have a different set of forces associated with it. It can also allow you to optimize the part to reduce its weight, and this could either be to reduce the cost of materials, or it could be to reduce the total weight for a part that, for example, needs to be lightweight in an aerospace application. Another thing that can often be considered in this program is manufacturability. So in some cases, a certain type of geometry will be difficult to produce using certain manufacturing methods, and by using the control functions for manufacturing method, it will make sure that the design it produces is something that can be done with whichever method you choose. So generally speaking, using generative design can allow you to save design and production time. It can save you material, improve strength, reduce mass, and a whole bunch of other things depending on what parameters you are able to optimize. So now getting into why is generative design so valuable to 3D printing and additive manufacturing in general. So one of the things that often occurs when you use generative design is that the optimal surface topology is going to result in a sort of complex organic looking surface. So you can see in the images at the bottom, these surfaces that were produced don't appear to have any clearly defined planes or right angles to them for the sections that were produced generatively. And this is, of course, because the optimal solution isn't going to be clean cut the way that a designer would produce it with their typical approaches. So the great value of 3D printing is that it isn't any more difficult to produce complex surfaces like this than it is to produce flat and clearly carefully angled surfaces. Whereas in other manufacturing methods, you often will find that complex surfaces like this become much more difficult and expensive to produce. So additive manufacturing can allow you to produce faster and cheaper parts, both for testing or low volume production. Can also apply constraints, and when you apply constraints to the surface of the part, then sorry, let me back up. So when you are when you're designing a part for a different type of manufacturing method, and you use the function that I mentioned on the previous slide, where you can control for different types of manufacturing approaches, that will allow you to still benefit from generative design. However, by including that constraint, it may take away from the optimization of the other parameters that you care about. So one point that actually makes generative design in some cases more valuable to other manufacturing methods is that typically you would design it for an isotropic type of material, and 3D printing has more trouble with producing isotropic parts than traditional manufacturing methods, where you're building from a block of some sort of stock material. So in the case of Rise, our material is not isotropic, but it is pretty close in terms of the horizontal and vertical strength. Compared to other 3D printing methods, Rise comes pretty close to isotropic strength. So here are some of the different programs that are created for or beginning to implement different types of generative design capabilities. So Paramatter's CogniCAD is a company that was produced specifically for generative design. And then you can see there are a few other major companies, SolidWorks, Autodesk, that are implementing it alongside their other functions. And this is certainly not an exhaustive list. Generative design is becoming a very popular technology, a very popular type of software. So there are companies producing generative design that are popping up all over the place. So whatever your requirements are, it's likely that someone is producing something that would be valuable to you. All right, so now to get into the nitty-gritty technical stuff a little bit, I'm going to talk about what generative design actually entails. So one of the things I mentioned earlier is that using generative design allows you to reduce the amount of expertise required to produce parts. So what I meant by that was that typically if you are designing a mechanical part, particularly a structurally important mechanical part, you need to have a certain amount of experience with mechanical design to ensure that the design you produce will sustain whatever forces are going to be exerted on it. And it typically takes years of training to be able to reach that level of expertise. So because generative design automates so much of the process of making decisions about where to place material and where to make things stronger and which places can be weaker, you don't need that level of mechanical design expertise. However, you will still need to have some knowledge of the program that you're using, because what generative design allows you to do is set up the sort of boundary conditions, or it allows you to set up the basic constraints of your system, and then it will create a design around that. So what you can see here in the picture is you start out by defining a set of obstacles, and that's colored in red. So these are regions where you don't want any material to be built. And then you produce a set of preserved geometry. So these are the areas that definitely need to include material. And these are the areas on the left in green. And then the next step is that you define a set of load cases. So as I mentioned, it may be that a part is only going to be used for one thing in one very specific action. And so you'll only need it to be able to sustain one type of load case. But if you are using a part that's going to be in a variety of situations, or it's going to experience some level of oscillation, then maybe you want to define a few different load cases that you want it to be designed for. The next step is to define your set of goals. So maybe you want to focus on strengthening the part, maybe you want to focus on minimizing material. This is also where you could choose what type of factor of safety you want the part to have. So on a part that is maybe in a structural section of a vital piece of equipment, probably you want a higher factor of safety than if it's just going to be a simple component of a small assembly. Next, you can select the set of materials that you want to be considered. And finally, as I've mentioned a few times, you get a bit of control in some cases over the type of manufacturing constraints that you want to use. So if you choose to use additive manufacturing, it will actually include a few constraints. For example, it will control things like the minimum thickness that it allows you to produce, and it might design things specifically to use self-supporting build angles so that you won't require as much support removal. These few things don't really affect the ultimate design that much. You can pretty much take full advantage of the optimized topology capabilities with these additive manufacturing constraints without losing much of your optimization of the other features like strength and material usage. On the other hand, if you use the constraints associated with subtractive methods, then it's going to be a bit more careful about the types of geometry it produces. So it will make sure that there aren't any of the types of sharp corners that can't be produced by a milling machine. It won't produce any internal cavities that can't be produced from a block of stock without digging into it. And it'll also make sure that the surfaces are something that can be produced with the types of tools that you would typically use under those manufacturing methods. So complex curved surfaces are fairly difficult to produce using normal milling machines, and it will avoid that type of geometry if you choose this option. So once you have defined your set of constraints, then what you do is you will generate a study, and this will give you a set of different solutions. Most of the technologies that are available right now do all of their calculations through cloud computing. This is because it's quite an intensive set of calculations that need to be done, a lot of iteration on complex geometries. So most that I'm aware of will use a pay per study type of subscription. So once you define your constraints, you export it to the cloud to be computed, and then you can go on using your machine for whatever other work you may have to do. So once it completes the study, it will notify you and give you a set of solutions. You can see here there are 6 different solutions shown for one type of part that was being produced. There are a few different types of solutions that the software may arrive at. The one that you are looking for is a converged solution. This is when it arrives at an optimal solution, and it is putting that forward as something that you would want to use. The other option is a completed solution. These are often cases where the part could not arrive at a solution and sort of moved around and got unstable and didn't produce something usable. So once you have the set of possible solutions, you want to go through them and maybe compare which ones are going to be most appropriate for your method of manufacturing, or most appropriate for maybe some other factors that you're aware of that you didn't include in the study. Another thing that you can do is, for perhaps a part that you don't intend to produce by additive manufacturing, maybe you need it to have a simpler geometry. One thing that you can use generative design for is that once you have a solution generated, then you can use the geometry that it gives you as sort of a basis, a form of guidance that you can use to design a part with a simpler geometry, but which covers all of the most important sections of the generated solution. All right, so those are all the major points that I wanted to cover. Just to do a quick review, we talked about limitations of traditional design methods and how generative design can sort of fill in the gaps that a lot of traditional approaches have. It can help you leverage the capabilities of additive manufacturing that maybe traditional methods haven't been able to harness in the past. There are a whole variety of different things that generative design is useful for. It can help you optimize a variety of parameters. It can help you save design and production time, save material, improve strength, and so on. It's especially useful for additive manufacturing because it tends to produce complex surfaces, which can cause a lot of trouble with traditional methods, but which are no more difficult for additive manufacturing methods to produce. And finally, I talked a bit about the more technical aspects of actually using generative design. So that's all the content I have for you today. If you have any questions, I'm going to stick around for a few minutes and you can type them into the chat box of GoToMeeting. As always, if you have any questions after we close out of this or anything off topic, you can always reach me at applications@rise3d.com.